that maybe this week we take a break from the math hazing and do a little video, with a little watching of a fluid mechanics film. So we'll do that on Friday. Let's just do that on Friday. Let's plan for this class. We do it during lecture hours. If I can book a bigger theater, then I'll do that and let you know. Otherwise, we'll just be in this class. Instead of, I was thinking about, I know I said pizza. I was just like, thinking out loud. But I think instead I'll just bring in some like little snacks, maybe some donuts, maybe some cookies, and I'll send out an email to see if you have any dietary preferences. So make sure we get for everyone. And I'll pick a film, from the fluid mechanics series, maybe a couple of them. Some of them are like 30 minutes long, and we can hang out and, watch them, discuss, ask questions. So take a break from the math routine. Okay? Does that sound like a good plan? All right. Okay. So last time we finished off with the Bernoulli equation. And can someone remind me what were the conditions under which we can apply Bernoulli? Okay, so conditions, implicitly saying Bernoulli equation. I mean, we can't apply the guy. Conditions for Bernoulli. Nick? Rho is equal constant along streamline. Inviscid. Okay. Inviscid. Anything else? So it applies along a streamline. Applies along streamline. And we concluded by saying that along a streamline, P over rho plus V squared over 2 plus rho G is equal to a constant, correct? That was the Bernoulli equation, right? Okay. Sorry, plus GZ. Whatever the height along that curve is, okay? And for a general flow where we can apply Bernoulli, we had different constants along different streamlines. So if this is streamline one, you had a constant C1. If this is streamline 2, this is constant C2. However, for irrotational flow, that constant was equal everywhere. So in an irrotational flow, you can apply Bernoulli equation between any 2 points. There's no need to have a streamline. Okay? C is, so equation is valid everywhere. Equation is valid everywhere. Okay? We'll do a couple of examples now to see how it applies. Hayden pointed something out to me last Friday, which was interesting. So I know we have not talked about viscous flows yet and the viscous stress tensor. But it turns out that if you assume irrotational flow, okay, then the viscous stress tensor actually becomes 0. It doesn't mean that the flow is inviscid. The flow mathematically can be viscous. However, the way the flow is structured, that viscous stress tensor, the net force due to viscosity, is 0. And then you can have the Bernoulli equation. So that way, you can essentially avoid having to make the assumption of inviscid flow. You can just say the flow is irrotational. But irrotational flow is more restrictive than assuming an inviscid flow. Okay, it's just like a mathematical trick. There's this guy called Joseph Daniel, I think his name is. He's always had these crazy papers that talked about viscous irrotational flow. You know, it's just kind of a little bit contradictory to some, but mathematically it is valid. If you assume the vorticity is 0, then the viscous stress tensor, the net viscous stress tensor disappears, but it doesn't mean that the flow is inviscid or doesn't have viscosity in it. Okay. Anyway, just a little point out of rigor. All right, let's do some Bernoulli equations, Bernoulli examples. Okay, the first and simplest example is, like I said, what my son might ask me one day, like we're out on a hike and he sees like this giant reservoir, and he asks me, what is the velocity of the flow at the bottom of the reservoir? So I have to grab, you know, a napkin and just do a calculation. This is the problem. Okay, so example 1, Bernoulli example 1 is just that. You have a little or a big reservoir, big tank, open to the atmosphere. So P atmospheric over here, atmospheric. And then there's an opening over here, and this is the water level, H, and then flow is coming out from over here. And this is also open to the atmosphere. And the question is, find this velocity over here. Okay. Now you ask yourself, does mass conservation help us in this case? Doesn't really, because you know, over here, there's barely any velocity. The flow is going down very slowly. This is a huge reservoir, right? Mass conservation might help you with H a little bit, but it will only give you a relation between the V exit and the V inlet, maybe. So you really need momentum over here to extract the velocity out. And momentum is essentially Bernoulli as far as we know now. So we assume the flow is nice and laminar and inviscid. And so, in other words, there's no crazy structures in the flow. It's nice and smooth. All the streamlines are kind of pointing out in this direction. They're just all going this way. So you pick a streamline and call this point 1 and call this point 2. I don't like it when the marker is not thick enough. We'll do the blue. Okay. And we apply Bernoulli between points 1 and point 2. And we say P1 over rho, P1 over rho plus V1 squared over 2 plus GZ1. What is Z1? We take our reference over here. So we say this is X, for example, and this is Z. Okay, so this would be Z1, and this over here would be Z2, okay, or 0. Doesn't matter, because what matters is going to be the difference, okay? So that's at point 1 equal to pressure at point 2, assuming density is the same along the streamline, right? Plus V2 squared over 2 plus GZ2. Okay. Now, both of these are open to the atmosphere, so their pressures are going to be almost constant, almost the same. You can pick a streamline, like right at the tip over here, it's open to the atmosphere. So you can knock out these two terms. Okay. At the surface, the velocity of the surface is so slow that we might as well just neglect it. Again, we're idealizing the heck out of this problem. So don't feel weird about making an assumption, okay? So we're gonna say that this is almost 0, V1, okay? So we knocked out this term. Then what we have is V2 squared over 2, okay, equal to GZ1 minus Z2, which is equal GH, right? That's the height of the tank at that point, okay? Now H is going to change with time eventually, But suppose that there's a river that's filling out the reservoir constantly, right? What we care about is this, the speed over here. That gives you V2 squared equal 2GH, and V2 equals square root of 2GH. That's a great formula to remember. You have like a little tank, a little bucket. You know, you want to get an idea of what the velocity is. Okay, the height of the bucket is h, then that's the velocity. Okay, pretty nice. Okay, so remember the Bernoulli equation is a momentum balance. Okay, so mass conservation, we have the continuity. We applied it in the integral form. We know the differential form. Okay, Bernoulli is like an integral version of the Euler equation. Okay, the integration though is along a streamline, but it's a momentum equation. Okay, think of it this way. Okay, so now we're going to take the same example and we're going to ask the question for an initial height of h0, whatever, how long is it going to take to drain this tank, right? So for every h, as h changes, your speed is square root of 2gh. And as h decreases, your exit speed is going to decrease as well. So you're draining it slower and slower over time, right? Not at the same initial speed. So what is that draining time? So if you remember, when we were doing mass conservation, we did a similar problem where we tried to derive an equation for the height of the tank as a function of time. Okay, so to do that, we need mass conservation because momentum is only giving us a value for the exit speed, right? What we need now is one additional formula that gives us the height, how the height is changing with time, and that comes from mass conservation. Okay, so I'm gonna consider that same tank. Okay, we apply mass conservation. So let's do example 2. Find time to drain tank filled with water with initial height h0. Okay, h0. So if you apply mass conservation, again we take the same surfaces we took when we did mass conservation. Probably we take this control volume with these control surfaces. Okay, the one shaded in green. These are terrible markers. Okay, so we had d by dt of integral of rho dv over the control volume, correct? Plus integral over the control surface of rho u dot n ds equal to 0. And if you remember that problem that we did last time, if the tank had an area AT, tank cross-sectional area, X for cross-sectional, okay? Then we had d by dt of rho times the volume, right, which was a tank, times h of t, function of time, right? Remember this problem, okay? Plus, the only exit we had was this velocity, okay, at point 2. So let's call it v exit, so times a exit, correct? And we have a rho v exit times a exit is equal to 0. So we drop out the density because it's assumed to be constant. A tank is constant, correct? A exit is constant, etc. So what we had last time was dH by dt is equal to minus V exit, what is it? A exit over A tank. Let me call it minus V2 A2 over A tank. Okay, so this is the formula we had last time. Okay, like I said, mass conservation just gives you this relation. Momentum is going to give you V2. Okay, so now we take that Bernoulli equation that we applied over there, V2, Bernoulli, for any instant in time, for any height h, that exit speed is going to be square root of 2gh. Correct? So V2 from Bernoulli is square root of 2gh of t, correct? Because for any height h, that's the exit velocity. So now we have h of t and h of t, and we have a differential equation, okay, for the height. We solve for the height, h of t, and then we find t when h is 0. And that gives you the t end, okay? So that's the plan. If you substitute, see what I had here. Now, think about this a little bit. Again, I repeat what I said when we did this problem in mass conservation. This is the rate of change of the height in time. On the right-hand side, you have a negative quantity, right? Because V2 is positive, A2 is positive, A tank is positive. There's a negative sign, so this whole thing is negative. And therefore, dH by dt is decreasing, okay? The negative slope, which is correct, makes sense because the height is decreasing, okay? All right, so what do I have here? Minus square root of 2gh A exit over A tank, which are measurable quantities, easily measurable, right? We get minus square root of h, square root of 2g, A exit over A tank. So you see how I integrated this over here. Just to, I mean, you can use your symbolic calculator if you want, but again, if you're stuck, you know, with your kid on Mount Timpanogos and you don't have access to Mathematica, you need to do this by hand. Okay, let me see how I did it. Okay, so here's what I did. I divided by square root of h and I multiplied by dt. So you get dh over square root of h, okay, is equal to minus square root of 2g A exit over AT dt. Really just a little mathematical trick, okay? So now I have homogeneous terms here, so I can integrate them easily. So if you integrate, and check this out. So we're gonna integrate here. For the left-hand side, we're integrating in h, correct? Because you have a dh. So what are the bounds of the integral? What is the initial h? Correct. Thank you. So we're integrating from h0 to 0, right? Of dh over square root of h equal to the integral from 0 to t end of minus square root of 2g ae over at dt. So now you see where t end showed up. So if you notice, t end corresponds to a height equals 0, and t0 corresponds to a height of h0. Okay? You do the integral. Let me erase over there. Okay. So again, this becomes just a math problem right here. So you get 2 square root of h from h0 to 0 equal minus square root of 2g, a exit over a tank, t from 0 to t end. And then from that, you can extract t end is equal square root of 2h0 over g, a tank over a exit. Okay. So when you're thinking about this problem, like, how the heck would you approach it, right? Why would you know that you can use this to get t end? You wouldn't. All you know is that you have some tools. These are the conservation laws. You know mass conservation, momentum conservation, energy conservation. Probably energy is not going to help you here. So you start writing down the mass conservation, and you get, the height is changing in time. You get a formula, and then you say, well, I don't know v exit. Let me put in v exit from momentum. You need another equation to get that other unknown, and it just kind of builds together. It just kind of aligns together, but you got to start acting. Okay. So it's okay to ponder and plan a little bit before you solve a problem, but sometimes you just have to get your hands dirty, really. And then you're like, I could have done it this way. Okay, but you need to get to that aha moment. You need to start doing something, okay? You need to start doing something. Don't be frozen when you're facing a problem in the exam or later on. Don't be frozen, just start writing something. Mass conservation, Bernoulli. Now you have tools under your belt, in your pocket, and start applying them and see what they give you. Okay? All right. Now I'm going to ask you to try to solve the following problem, and I'll walk around and chit chat with you. Okay, so this next problem example 3. You have a little hose jet that is pushing some water out, okay? And it's more like dripping, okay? It's more like dripping. And as the water comes out, it kind of thins down, right? So it's coming out jet with a diameter d1 initially, okay? And, suppose, for example, this would be the exit velocity of the tank. So you could say v1 is equal square root of 2gh, whatever h is, okay? So you have a velocity v1 over here. It's known. You know that velocity, okay? Now the question is, find the diameter at a height h. So this is a different h. Let's call this capital H. At a height h, okay, from the outlet of the jet. Okay, so don't worry about v1. Just keep v1 as is. So this is diameter d2. Okay. The question is, what is d2? Express it in terms of d1 and v1. Okay. You can work in groups. Okay. Again, see what mass conservation gives you, see what momentum gives you. This is a simple mass conservation problem, density is constant. So A1 V1 is A2 V2, right? So you can just write that down. Don't worry about proving it. And then let's see what you can do with it. Okay? Go ahead and work in groups. I'm going to hide this. I'm going to hide. Sorry. Yeah, so assume the area is cylindrical. Okay, so diameter d1. So a1 is pi d1 squared. Okay, area a1.
The same one?
Can you assume that they're the same pressure?
There what?
They're the same pressure.
That's the most important assumption. Yes, because atmosphere. So yeah, you're missing a four. I wrote it wrong. So pi d1 squared over four, right? Or pi r1 squared. Sorry, but it's not gonna matter because it's gonna cancel out.
D1 to D2 to the 2, and we also have the square, so it's, I think, 4. Well, yeah.
So start with mass conservation. Mass conservation will give you d2, right? Immediately. But then there's something missing in there, right? There's gonna be a v2. So how do you get v2? So assume steady state. So you do, yeah, assume steady state. Mm-hmm.
So from the mass conservation, we know that this is
Mm-hmm.
true, and we can also put this one here, V2, as related to V1. But
Mhm.
if it cancels with V1, and we do have the D1 in terms of D2.
Are you sure it cancels out? It doesn't cancel. You have a plus over here.
Oh, yes.
Any progress?
So situation said that this term doesn't exist because this term is zero.
Okay, so let me give you mass conservation. Don't overdo mass conservation. Mass conservation is simply A1 V1 equal A2 V2. Okay? You're looking for D2, so pi D1 squared V1 over 4 equal pi D2 squared over 4 V2. So you get D2 squared equal D1 squared V1 over V2. You know V1, you know D1. What is V2? Okay. Do you wanna continue, Ali?
Yeah, I can.
Okay.
So V1 squared over 2.
Okay. So you take a streamline. Let's formalize it. Okay. Let's make it rigorous. Okay. Consider a streamline. Assume that the flow is inviscid and that there are nice streamlines. Consider a streamline, say at the center of this jet, from point 1 to point 2. Okay. Now apply Bernoulli. Okay. So what do you get? V1 squared over 2. Well, there's a P1 over rho. We need to cancel that, right? So there's a P1 over rho plus V1 squared over 2. So, okay. So you're considering that this is Z2 and this is Z1. Okay. So I'm going to write it as, sorry, this is Z1 and this is Z2. Okay. Plus GZ2. Okay. So what do you do with the pressures?
I cancel that because the pressure equals.
Because your point is just at the atmospheric pressure, right? So you can, that's the biggest assumption you're going to make. Okay. Once you do that, then we get, remember we're after V2, correct? So you get V2 squared over 2 equal V1 squared over 2 plus GH, correct? So GZ2, GZ1 minus GZ2 squared, and then you get V2 squared equal V1 squared plus 2GH, and V2 equals square root of V1 squared plus 2GH, correct? Is that what you got? Okay. Now, simply put V2 over here. So V2 over here, you get V1 squared times V1 over square root of V1 squared plus 2GH. If you had started with Bernoulli, you would still have had the problem of saying, so you would have obtained V2, but that's it. Nothing, no area. Where does the area come in from? Mass conservation, right? So I will start with mass conservation. And really, the answer is from mass conservation. The only thing we were missing was the V2, because that's what momentum gives you. Okay? Let's do one more example. Okay? So we're going to take that same jet. I'll give you a minute to. And this is described on the permanent lectures very carefully. So, if you miss something here in the discussion, you can see it over there. So then you start seeing a trend. If you're calculating an area, a thickness, a length, you need mass conservation, okay? And momentum, because momentum is going to give you the missing piece, one of the velocities. If you're only looking for the velocity, you need momentum. That's it, okay? So this is a similar problem, except that you have a pool of oil, okay, or some other liquid, okay? Call it oil. And then you have a little opening over here. And there's some water drizzling down, water coming in diameter d1 and a speed v1, okay? and there's oil over here. Okay. Assume that the density of oil is raw oil, and the density of water is raw water. Okay. Now the question is, so at some height h, you have a velocity here, v2. Okay. The question is find v2. Okay. The question is find v2. So let's work this through together. Okay. Like I said, when there's no area or diameter involved, you probably only need momentum. You can write mass conservation. It's not going to give you anything related to the velocity. It just tells you that A1 V1 is A2 V2. So really here to find V2, we need momentum. Okay. So again, we consider that the flow is steady in viscid, nice streamlined structures, and we consider a streamline from point 1 to point 2 over here. And we write the Bernoulli equation. That's P1 over rho water, because we are in water, correct? I want to distinguish raw water from raw oil, plus V1 squared over 2 plus Z1. So this would be Z2 and this would be Z1 equal P2 over rho water plus V2 squared over 2 plus GZ2. What do we know and what do we not know in this equation? So we know GZ1, we know GZ2, we know V1, okay? We're after V2, but do we know P2 and P1? This is not in air, this is in oil, a heavy liquid. So if you move a little bit in oil, you're going to sense a difference in pressure. So could you, in previously when we were in air, we said, you know what, P2 and P1, they're almost identical. Because you're open to the atmosphere, there's not a significant change over short distances, but now you're in oil. Can you say that P2 and P1 are equal? You cannot. P2 is not equal to P1. So you have 1, 2, 3 unknowns in one equation. Or you have 2 unknowns and one equation because all you need is P2 minus P1. So what do you do in this case? There's a little trick from statics. You say that, well, from statics, we know that the pressures at the same level must be equal necessarily. So the pressure anywhere at this level, so the pressure here must be equal to the pressure over here. And the pressure over here must be equal to the pressure over here. So you take a point in oil, okay? You take a point in oil and get the pressures from the oil, okay? And again, from statics, we know that P1, so statics, P1 is, what's that formula? Okay. It's raw oil, G, whatever H is above you. Or actually, let me do it in a better way. From statics, you say that P2 over here is equal to P1 over here. You say that P2 is equal to P1 plus the weight of this mass of oil, which is raw oil times G times H. And that gives you, put P2 minus P1 or P1. That gives you P2 minus P1 is equal to raw oil GH. Full trick, you know, when you're, that's kind of one of the only few cases where you cannot knock out the pressure term in Bernoulli because you're not in the atmosphere. Okay? It's just that simple realization from fluid statics that these lines are constant pressure. They're the same pressure. This line is same pressure, this line is same pressure. So what we have to do is jump out into the oil and do this assumption. You cannot do this within the jet because P2 is not in the jet. P2 is not equal to P1 plus mass of the jet because there's other things going on in the jet. It's not static. It's moving. There's potential energy and there's kinetic energy. But in the oil is stagnant. There's no other thing going on in the oil. Make sense? So you couldn't do this with water. P2 minus P1 is not equal to raw water GH because the jet is not static. It's moving. But the oil is. If you go far away from the jet, the oil is static. Okay, so you can make this assumption. And then when you do all the math, you get an equation for the velocity. V2 squared is 2 times 1 minus raw oil over raw water. Okay, GH plus V1 squared. Okay. Now consider, okay, what was the other equation? Okay. Now, can you make, so look at this equation. This is the equation of the velocity, this one. Compare this equation to that equation. Can you make the two equal? This is the velocity of the jet when it was immersed in air. This is the velocity of the jet when it was immersed in a other fluid that is heavy. Can you consolidate the two? So this should be a special case of that one, right? How? Okay, you answered a lot today, Ellie, and I feel bad to get more answers from you. Sam, do you want to take it? When they're equal? Okay, so what does that mean? So raw water stays raw water, but what happens to the surrounding fluid? What is the density of air compared to water? Density of air is like 1, density of water is 1,000, right? So when this ratio goes to 0, right? Yeah. So what they said is that if this ratio approaches 0, in other words, or 1 minus rho outside fluid, outer fluid, over rho water is approximately equal to 1. So this guy is negligible. And that happens when the denominator is much higher than the numerator in value, right? Or the numerator is much smaller. And then you get that one. That's cool, right? That makes you happy, makes me happy that, you know, my answers are consistent, right? Okay, keep that little trick in mind, because that's one of the few cases where you cannot knock out the pressure term in Bernoulli, in the Bernoulli equation, okay? And that's it for Bernoulli. There's nothing much more you can do with it, okay? So this equation approaches that equation, and the limit as rho oil goes in the limit that rho oil over rho water goes to 0, okay? All right. We're done with Bernoulli. Our next step on Wednesday, we're going to start deriving the full equations we're going to add the viscous stress tensor. We'll spend some time talking about the viscous stress tensor, how it looks like, well, the structure of a tensor without really digging into what the value is. Well, we'll expand it, we'll put in the equation, we'll derive the equation using the Reynolds transport theorem, doing a shell balance, doing different interpretations for the stress tensor, whether it's a force or a diffusion tensor. We'll know what the tau ij means, etc. We'll do the derivation, and when we'll have the full viscous flow equations, we'll spend the rest of the semester talking about those. We're going to circle back to potential flow theory, okay, which is weird. We're going to do it later because when you put omega equals 0, things happen in the governing equation, and you get potential flow theory. It really gets more interesting, okay? Thank you so much, and I will see you on Wednesday.